This video is going to be on action potentials. I've done some previous videos on action potentials. This one is going to be specific to action potentials within a neuron and graded potentials associated with that. And this will also be an adjunct to my most recent video, which I did on equilibrium potentials, specifically the equilibrium potential for sodium, which is positive 60, and the equilibrium potential of potassium, which is negative 90, or roughly negative 90. Some textbooks will suggest it's negative 91, negative 93. But for our purposes, we're just going to suggest it is negative 90. Okay, so let's take a look at the graph here. What we see here on the x-axis is time, y-axis is millivolts. The resting state of neurons tends to be about negative 70 millivolts. It can be variable depending on the neurons, but for our purposes, let's just suggest that the resting state or the resting membrane potential for the neuron is negative 70 millivolts. So we've talked about action potentials. We outlined what an action potential looks like on a graph, and this is going to look similar to it. But one thing I didn't really touch on specifically was a concept known as threshold. And I guess we have talked about it in previous videos, where an action potential that's initiated at the axon hillock, the point where the axon is departing from the cell body, the voltage that must be reached to activate the first sodium-gated channel at the beginning of the axon must reach negative 55 millivolts to cause that all or nothing event, which is the progression of that action potential from the axon hillock all the way down to the axon terminals. Once again, that voltage is negative 55 millivolts, which is caused by a graded potential, which we see here in green. A graded potential is a depolarization event that travels across the cell body of a neuron, initiated at the dendrites. The dendrites have a number of ligand-gated, potentially mechanically gated ion channels, specifically sodium ion channels. The influx of the sodium is going to cause a depolarization event across the cell body. But one big difference between graded potentials and action potentials is graded potentials vary with the strength of the initial stimulus. So here we have a graded potential in green, but if that initial stimulus is not strong enough, the graded potential may not reach threshold at negative 55 millivolts. And if we don't reach threshold at negative 55 millivolts, then we will not proceed to have a full action potential. But if we do reach threshold at the axon hillock, negative 55 millivolts, we can be certain we're going to have an action potential down the axon. That action potential, the depolarization phase of the action potential, which is due to sodium influx, will reach 30 millivolts. Now, in a previous video, we talked about sodium's equilibrium potential. This does not reach sodium's equilibrium potential because those sodium gates close, and as a result, sodium is not given the opportunity to make it up to positive 60 millivolts. After we hit positive 30 millivolts, the cell proceeds to repolarize due to the efflux of potassium. And this is pretty interesting here, as we see as potassium leaves, the cell becomes progressively more negative, going back to the resting state. But as we see right here would represent the resting state. So this is roughly negative 70 millivolts. But as we can see, the repolarization continues beyond the resting state to create what's known as a hyperpolarization. That is to say, it's going beyond negative 70 all the way down here, that's roughly negative 90. And that corresponds to potassium's equilibrium potential. The reason why this cell does not hyperpolarize beyond negative 90 is because potassium has reached its equilibrium potential. And theoretically, those potassium channels are still open, but potassium will not leave the cell any longer because the cell has become so negative inside potassium is incentivized to stay inside the cell where it's super negative. Potassium is positive. Positive and negative are attracted to each other. So negative 90 is where hyperpolarization ends, not because the potassium channel is closed, but because that is potassium's equilibrium potential. And then eventually that will move back up to the resting state of negative 70. So that's a typical action potential, or I should say that's typical electrical activity or excitation of a neuron that incorporates both the graded potential and the action potential.